You're listening to Animal Uncovered. This is a spoken word compilation meant to be played in the dark. There are no sound effects, no music, and nothing you need to follow. You can let the words pass without holding on to them. If your mind drifts, that's exactly what it's supposed to do. Get comfortable. I'll keep speaking for a while. You don't need to stay awake. In the depths of our planet's most alien realm, where sunlight has never dared to venture, a creature of impossible intelligence dwells in solitude. It possesses 3 hearts that pulse with ancient rhythms, blood as blue as the deepest ocean trenches, and a mind so sophisticated it can solve puzzles that baffle creatures with lifespans 10 times its own. Yet this master of disguise, this underwater genius, lives by a biological clock so cruel, so unforgiving, that it transforms every moment of its existence into a race against time itself. Welcome to Animal Uncovered. I'm your narrator, and today we dive into the extraordinary world of the octopus, a creature whose life story reads like a tale of brilliance, sacrifice, and the most exquisite tragedy nature has ever written. Chapter 1. The Dance of Death. Picture, if you will, the rocky crevices of the Mediterranean seabed. Here, in the twilight realm where shadow meets stone, a male octopus emerges from his den. He is Octopus vulgaris, the common octopus, though there is nothing common about what he's about to do. His skin ripples with colours that speak a language older than words. Reds cascade into browns, whites flash like lightning across his mantle. He's searching, driven by an ancient imperative that will seal his fate. For in the world of the octopus, love is quite literally a death sentence. The female he seeks is larger, more powerful, her den a fortress of carefully arranged shells and stones. She could easily mistake his approach for that of prey. One wrong move, one misread signal, and she would consume him before he could fulfill his purpose. But evolution has equipped him with one of nature's most extraordinary solutions. Hidden beneath his skin, coiled like a secret weapon, lies his hectocotylus, a specialized arm that serves as both his reproductive organ and his final act of devotion. As he approaches her den, his skin flickers with what can only be described as nervous energy. The female, 3 times his size, watches from the shadows. She has seen suitors before. Many have not survived the encounter, but this male is different. Perhaps it's the urgency in his movements, or the desperate beauty of his colour display, but she allows him to approach. What happens next is one of nature's most intimate and tragic exchanges. The male extends his hectocotylus, this specialized arm, toward the female. In a process that takes mere minutes, he transfers packets of sperm, called spermatophores, into her mantle cavity. It is a moment of biological poetry, this passing of genetic material in the cathedral darkness of the ocean floor. But the price is absolute. The male's hectocotylus detaches, literally breaks away, remaining inside the female as he retreats. He is given not just his genetic material, but a piece of himself. Within days, perhaps hours, he will die. His body will shut down, his colours will fade, and the ocean will reclaim him. For the female, this is only the beginning of her sacrifice. Chapter 2. The Mother's Vigil. In the weeks following mating, the female octopus undergoes a transformation that would humble any human mother. Her body begins to swell with eggs, thousands upon thousands of them, each no larger than a grain of the rice, yet each containing the complete blueprint for one of nature's most sophisticated creatures. She seeks out the perfect nursery, a cave, a crevice, or the underside of a rocky overhang. Here, she will create what marine biologists call a brooding den, a fortress that will become both sanctuary and prison. The eggs emerge in translucent strings, like nature's own DNA helixes made visible. The female tends to each strand with the devotion of a master craftsman, using her 8 arms to arrange them in perfect cascades. She blows water over them, ensuring they receive the oxygen they need to develop. She tends them with a gentleness that seems almost impossible from a creature that can crack crab shells with ease. But here begins the most extraordinary sacrifice in the animal kingdom. From the moment she lays her eggs, the female octopus enters what scientists call reproductive senescence, a biological program that will ensure her dedication to her offspring at the cost of her own life. She stops eating entirely, not occasionally, not when food is scarce. She stops eating forever. Her body begins to consume itself. Muscle mass decreases. Her skin loses its vibrant colours. Her once powerful arms grow weak. Yet she never leaves her post. For 6 months, perhaps longer, she will guard those eggs with supernatural dedication. During this vigil, she faces constant threats. Hungry crabs scuttle past, drawn by the scent of developing life. Fish probe the entrance to her den, seeking an easy meal. But the mother octopus remains steadfast, using her weakening arms to brush away intruders to maintain the water flow that keeps her eggs healthy. It is a biological tragedy of Shakespearean proportions. The very act of reproduction triggers her death sentence, yet she embraces it with a devotion that speaks to something profound in the architecture of life itself. And then, after months of this selfless vigil, the miracle begins. Chapter 3. The Awakening. It starts with the faintest of movements, a barely perceptible trembling within the translucent eggs. After months of development, fueled by the nutrients their mother's body provided, the baby octopuses are ready to emerge. What hatches is not a miniature version of the adults we know, but something far more extraordinary. These creatures, called paralarvae, are no larger than a pinhead, yet they are already perfect predators. They emerge with functioning eyes, working chromatophores for colour change, and 8 tiny arms equipped with suckers ready to grasp the microscopic world around them. The mother, now at the very end of her strength, performs one final act of devotion. She blows water over the eggs, helping her offspring break free from their translucent prisons. As they emerge, thousands of them, like tiny jewels scattered in the current, she ensures they are swept away from the den and into the open ocean. It is her last maternal act. Within hours or days of this mass hatching, the mother octopus will die. Her body, consumed by months of starvation and the biological imperative to reproduce, finally surrenders to the sea. But her offspring face their own incredible journey. These paralarvae, each weighing less than a milligram, must now survive in the vast 3-dimensional wilderness of the open ocean. They join the plankton, that floating community of microscopic life that forms the foundation of all marine ecosystems. Here, in the plankton cloud, they are both predator and prey. Their tiny arms reach out to capture even tinier creatures, copepods, marine larvae, microscopic crustaceans. Their eyes, already sophisticated despite their size, track movement in the water column with precision that would impress any human engineer. But the ocean is vast, and these tiny octopuses are utterly alone. Unlike many marine animals whose parents guard them, teach them, or provide them with food, These paralarvae must learn everything from scratch. They must discover what is food and what is predator, what is shelter and what is trap. The mortality rate is staggering. Of the thousands that hatch, perhaps only 1 or 2 will survive to adulthood. They face an endless array of threats: jellyfish with trailing tentacles, fish with mouths that can engulf dozens of them at once, and countless other predators that see them as nothing more than floating protein. Yet those that survive begin to exhibit something remarkable: the first signs of the intelligence that will define their species. Chapter 4: The Education of a Genius. After weeks in the plankton, the surviving paralarvae undergo one of nature's most dramatic transformations. They settle to the ocean floor, their bodies changing from transparent drifters to the complex muscular forms we recognize as octopuses. But they are still tiny, no larger than a human fingernail, and now they face an entirely new set of challenges. The seafloor is a landscape of predators and competitors, where every rock, every crevice could hide either refuge or death. It is here that the octopus's legendary intelligence truly begins to manifest. Watch a juvenile octopus explore its environment, and you witness one of nature's most sophisticated learning processes. Unlike most invertebrates, which rely primarily on instinct, young octopuses exhibit what can only be called curiosity. They investigate objects, manipulate them, test their properties. They are, in essence, conducting experiments. Their skin becomes their first tool of survival. Those remarkable chromatophores, specialized cells containing pigments, allow them to change not just color, but texture as well. They can mimic the appearance of coral, algae, rocks, even other animals. A young octopus might cycle through dozens of different camouflage patterns in a single minute, each one a potential lifesaver. But perhaps most remarkably, they begin to use tools. In the waters off Indonesia, marine biologist Mark Norman made a discovery that revolutionized our understanding of invertebrate intelligence. He observed octopuses collecting coconut shells, cleaning them, and carrying them across the seafloor. When threatened, they would assemble these shells into protective shelters, essentially creating portable homes. This behavior requires not just intelligence, but planning. The octopus must envision future danger, recognize the protective value of the shells, and execute a complex sequence of behaviors to achieve its goal. It is a level of cognitive sophistication that we once believed was exclusive to vertebrates. As they grow, their learning accelerates. They develop individual personalities, some bold and exploratory, others cautious and methodical. They learn to recognize individual fish, remembering which species are dangerous and which are prey. They develop hunting strategies, often specific to their particular environment. A Mediterranean octopus might specialize in cracking open sea urchins, while a Pacific species perfects the art of mimicking flatfish. Each individual becomes a specialist, adapting its behavior to the unique challenges of its habitat. But perhaps most extraordinarily, they appear to learn from observation. Young octopuses have been observed watching other octopuses hunt, then incorporating those techniques into their own behavior. They are, in essence, teaching each other. Chapter 5: Masters of Deception. As the octopus matures, it develops into what can only be described as a living masterpiece of biological engineering. Its skin becomes a canvas capable of producing displays that would make any human artist weep with envy. The secret lies in those chromatophores, millions of them, each containing pigments that can be expanded or contracted in milliseconds. But that's only the beginning. Beneath the chromatophores lie iridophores, cells that reflect light and create metallic sheens. Deeper still are leucophores, which produce white coloration and can amplify the effects of the other cells. The result is a creature capable of what marine biologists call dynamic camouflage, the ability to change appearance faster than the human eye can follow. An octopus can shift from the mottled brown of a rocky reef to the pure white of sand, then to the rippling patterns of sunlight filtering through kelp, all in the space of a heartbeat. But this is not mere camouflage, it is transformation. The octopus doesn't just match its environment, it becomes it. Its skin can project three-dimensional textures, creating the illusion of coral branches, algae fronds, or rocky surfaces. It can even mimic the movement patterns of other creatures, undulating like a flatfish or flowing like a piece of kelp in the current. Perhaps most remarkably, octopuses have been observed using what researchers call progressive camouflage, moving across different environments, while continuously adjusting their appearance to match each new background. It's as if they possess an internal map of their territory, complete with a catalogue of appropriate disguises for each location. But the octopus's intelligence extends far beyond camouflage. They are problem solvers of extraordinary ability. In laboratory settings, octopuses have learned to navigate complex mazes, unscrew jars from the inside, and even escape from their tanks to explore their surroundings, sometimes returning to their enclosures before their absence is discovered. One famous octopus named Inky escaped from New Zealand's National Aquarium by squeezing through a gap in his tank, crawling across the floor and disappearing down a drain that led to the ocean. The entire escape was captured on security footage, revealing a level of spatial awareness and problem-solving that astonished researchers. In the wild, their intelligence manifests in countless ways. They use tools not just defensively, but as hunting aids. Some species have been observed using rocks as hammers to crack open shellfish, while others employ sticks to extract prey from crevices. They modify their environment, building dens and garden areas around their homes. Perhaps most intriguingly, they appear to plan for the future. Researchers have documented octopuses collecting materials and storing them near their dens, apparently anticipating future needs for shelter construction or tool use. Chapter 6. The Hunt. When an octopus hunts, it becomes a creature of liquid grace and calculated violence. Its 8 arms work in perfect coordination, each one capable of independent thought and action. Scientists have discovered that octopus arms contain their own neural networks, essentially mini-brains that can taste, touch, and react without input from the central brain. Imagine having 8 appendages, each with its own intelligence, working together toward a common goal. It is a form of distributed consciousness that we can barely comprehend. The hunt begins with reconnaissance. The octopus emerges from its den like a shadow given form, its skin already adapting to the terrain. Its eyes, as sophisticated as any vertebrates, scan the environment for the telltale signs of prey. Unlike human eyes, which move to track objects, octopus eyes remain fixed while the pupils, shaped like rectangles, adjust to maintain perfect focus. When prey is detected, the transformation is instantaneous. The octopus becomes a living weapon, its arms extending with hydraulic precision. It can attack from multiple angles simultaneously, with some arms grasping prey while others maintain camouflage or prepare escape routes. But perhaps most remarkable is its ability to predict prey behavior. Researchers have observed octopuses positioning themselves not where their prey currently is, but where it will be moments later. They are, in essence, thinking several moves ahead, a cognitive ability that rivals that of much more complex vertebrates. The kill itself is swift and efficient. The octopus's beak, a structure harder than steel, delivers a precise bite that injects both toxins and digestive enzymes. The prey is paralyzed and begins to dissolve from within, allowing the octopus to consume it without the need for chewing. 30. But the octopus faces its own predators, and here its intelligence truly shines. When threatened, it can employ a bewildering array of defensive strategies. The famous ink cloud is just one option, a smoke screen that not only obscures vision, but also contains compounds that interfere with predators' chemoreception abilities. Some octopuses have developed even more sophisticated defenses. The mimic octopus can impersonate other species entirely, taking on the appearance and behavior of flatfish, lionfish, or even sea snakes. It's as if they maintain a mental library of other creatures, selecting the most appropriate disguise for each situation. Perhaps most remarkably, octopuses have been observed using what can only be described as misdirection. They will create elaborate displays with some arms, while using others to prepare escape routes or defensive positions. They are quite literally master magicians of the marine world. Chapter 7. The Cruel Mathematics of Time. But here we encounter the cruel paradox at the heart of the octopus's existence. All of this intelligence, all of this sophisticated behavior, all of these remarkable adaptations, they are compressed into a lifespan that rarely exceeds 2 years. Consider the implications of this biological tragedy. While a human child is just learning to walk, an octopus has completed its entire life cycle. While we are still developing our cognitive abilities, the octopus has already mastered skills that would challenge adult humans, reproduced, and died. This brevity creates what scientists call evolutionary pressure for rapid learning. Unlike creatures that can rely on experience accumulated over decades, octopuses must become experts in survival within months of settling on the seafloor. They cannot afford the luxury of gradual learning. Every day is precious, every lesson potentially life-saving. 34. The result is a creature that seems to live in fast-forward, packing lifetimes of experience into months of existence. They mature rapidly, reaching sexual maturity within their first year. Their learning curve is unlike anything else in the animal kingdom, steep, intense, and absolutely essential for survival. This temporal compression may explain their remarkable intelligence. When you have only months to master the skills necessary for survival and reproduction, every cognitive advantage becomes crucial. The octopus's brain, with its 500 million neurons, represents evolution's solution to the problem of maximum intelligence in minimum time. Yet this same intelligence makes their brief lifespan all the more poignant. Here is a creature capable of complex problem-solving, individual personality, and sophisticated communication, yet it is granted less time than a human toddler to explore the world. Some researchers have suggested that octopuses represent a different evolutionary path to intelligence, one based on intensity rather than longevity. While mammals developed large brains to accumulate knowledge over long lifespans, octopuses evolved sophisticated neural networks to maximize learning within the constraints of brief existence. Chapter 8. The Final Season. As the octopus approaches its final season, its behavior begins to change. The urgent hunting, the careful den maintenance, the constant vigilance, all of these gradually give way to a different imperative. The drive to reproduce begins to dominate all other considerations. For the male, this means seeking out a mate, despite the certain knowledge that this encounter will be his last. The female, meanwhile, prepares for her own sacrifice, her body already beginning the biological changes that will ensure her devotion to her offspring. It is here that we see perhaps the most profound expression of the octopus's intelligence, not in problem-solving or tool use, but in the apparent acceptance of their fate. They seem to understand in some fundamental way that their time is limited, and they use every moment to ensure the survival of the next generation. The mating ritual, when it occurs, is both beautiful and tragic. The male approaches with displays of colour and pattern that represent the culmination of his brief existence. Every hue, every texture, every gesture is a desperate attempt to communicate his worth as a partner. The female, larger and more powerful, holds his life in her arms, literally and figuratively. After mating, the transformation is swift. The male's body begins to shut down almost immediately. His colours fade, his movements become erratic, and within days, he will join the countless generations of his species that have made this ultimate sacrifice. For the female, the process is more gradual but no less certain. As her eggs develop, her body enters that remarkable state of reproductive senescence. She will spend her final months in devoted guardianship, using her remaining strength to ensure the survival of thousands of potential offspring. It is a biological imperative so strong that it overrides even the most basic drive for self-preservation. She will literally starve herself to death to ensure the survival of her young, a sacrifice that humbles our human understanding of parental devotion. Chapter 9. The Eternal Cycle. And so the cycle completes itself, as it has for millions of years. The mother's death coincides with the hatching of her offspring, ensuring that her final breath gives life to the next generation. Those tiny paralarvae, each carrying the genetic wisdom of their parents, begin their own perilous journey through the vast ocean. Most will not survive. The ocean is unforgiving, and the odds are stacked against them. But those few that do survive carry within them the accumulated intelligence of their species, the ability to learn, to adapt, to solve problems, and to transform themselves into masters of their environment. In the grand theatre of ocean life, the octopus represents something unique, a creature that achieves in months what other animals might take years to accomplish. They are living proof that evolution can create intelligence through intensity as well as longevity, that consciousness can burn bright and brief like a shooting star. Each generation of octopuses faces the same challenges their ancestors did: predators to avoid, prey to catch, mates to find, and young to protect. Yet each generation also brings new adaptations, new behaviours, new solutions to the eternal problems of survival. They are in many ways the ocean's greatest success story. Creatures that have mastered their environment not through size or strength, but through intelligence and adaptability. In their brief lives, they accomplish feats that would challenge creatures with much larger brains and much longer lifespans. The octopus reminds us that intelligence is not the exclusive domain of long-lived creatures. In the vast laboratories of the ocean, evolution has created a form of consciousness that burns bright and brief, like a candle in the darkness of the deep. Chapter 10. Reflections on the Alien Mind. In studying the octopus, we encounter something that challenges our most basic assumptions about intelligence and consciousness. Here is a creature whose last common ancestor with humans lived over 500 million years ago, yet it exhibits behaviors that seem startlingly familiar. Curiosity, problem-solving, individual personality, and complex communication. This convergent evolution of intelligence suggests something profound about the nature of consciousness itself. Perhaps the ability to learn, to adapt, to solve problems represents a fundamental property of complex life, one that can emerge independently in vastly different lineages. The octopus's intelligence operates through neural networks that are radically different from our own. While our intelligence is centralized in a single brain, theirs is distributed throughout their body. Each arm contains its own neural networks, capable of learning and responding independently. It is a form of consciousness that we can barely imagine, embodied intelligence that experiences the world through 8 semi-independent appendages. Their perception of the world is equally alien to our experience. They see polarized light patterns invisible to us, taste through their skin, and communicate through colors and patterns that create a visual language of extraordinary complexity. In many ways, they inhabit a sensory universe that overlaps with ours, but extends into dimensions we cannot perceive. Yet in their brief lives, they achieve a level of environmental mastery that speaks to something universal about intelligence. They modify their surroundings, use tools, plan for the future, and adapt their behavior based on experience. They are, in essence, engaging with the world in ways that we recognize as fundamentally intelligent. The octopus forces us to expand our definition of what consciousness might look like. It suggests that intelligence can emerge from different evolutionary pressures, operate through different neural architectures, and manifest in ways that are both alien and familiar. Chapter 11. The Deep Mysteries Remain. Despite decades of research, the octopus continues to surprise us. New species are discovered regularly, each with its own unique adaptations and behaviors. The deep-sea octopuses, living in the eternal darkness of the ocean depths, have developed strategies for survival that we are only beginning to understand. Some species brood their eggs for years, not months, a remarkable exception to the rule of brief lifespans that defines most octopuses. Others have developed bioluminescence, creating their own light in the darkness of the deep. Still others have evolved to live in environments so extreme that they challenge our understanding of what life can tolerate. The giant Pacific octopus, largest of all octopus species, can live for up to 5 years and grow to span 30 feet from arm tip to arm tip. These ancient creatures, living in the cold waters of the North Pacific, represent the exception that proves the rule, showing us what octopus intelligence might achieve given more time to develop. But even our most sophisticated research methods can only scratch the surface of octopus consciousness. How do they experience the world through their distributed nervous system? What is it like to possess 8 semi-independent arms, each with its own capacity for learning? How do they integrate information from skin that can taste, eyes that can see polarized light, and arms that can think? These questions remain largely unanswered, reminders that the ocean still holds mysteries that may forever elude our understanding. The octopus represents not just a triumph of evolution, but a window into forms of consciousness that operate according to principles we can barely imagine. In their alien intelligence, we glimpse the vast possibilities of life itself, the countless ways that consciousness might emerge, develop, and express itself in the universe. They remind us that intelligence is not a ladder with humans at the top, but a vast landscape of possibilities, each shaped by the unique pressures and opportunities of different environments. Closing. the insane genius of the deep. And so we return to where we began, to the mystery of a creature that lives an existence so compressed, so intense, that it seems almost impossible. In the span of a single human year, an octopus is born, learns to hunt, masters the art of camouflage, develops its own personality, finds a mate, reproduces, and dies. It is a life that unfolds like a time-lapse photograph of intelligence itself, every moment precious, every experience essential, every decision potentially the difference between survival and extinction. The octopus's brief existence reminds us that consciousness is not measured in years, but in the intensity of experience. In their fleeting lives, they demonstrate capabilities that would challenge creatures with lifespans 10 times their own. They are problem solvers, communicators, artists of camouflage, and masters of adaptation, all compressed into a time frame that barely allows for a single human childhood. Perhaps this is what makes the octopus so extraordinary, not just their intelligence, but the impossible pace at which they must deploy it. They are evolution's answer to the question, how much consciousness can be packed into the briefest possible existence? The answer, as we have seen, is more than we might ever have imagined. In their alien intelligence, their impossible adaptations, and their tragic beauty, octopuses represent one of nature's most profound achievements, a form of consciousness that burns bright and brief in the vast darkness of the ocean. They live insane lives, insane in their intensity, their intelligence, their devotion to the next generation. They are creatures of genius and sacrifice, of intelligence and tragedy, of beauty and loss. And in the end, perhaps that is what makes them so remarkable. They remind us that consciousness itself is a kind of miracle, a brief flowering of awareness in the vast universe, precious precisely because it is so fleeting. In the depths of our oceans, where light has never ventured and pressure would crush human bones, the octopus continues its ancient dance of intelligence and sacrifice. New generations emerge, learn, adapt, and pass on their genetic wisdom to the next wave of these remarkable creatures. They are the ocean's philosophers, its problem solvers, its artists of transformation. In their brief, brilliant lives, they illuminate the endless creativity of evolution and the profound mysteries of consciousness itself. The insane life cycle of the octopus, genius compressed into tragedy, intelligence racing against time, love literally unto death, continues in the eternal darkness of the deep. And we, in our human understanding, can only marvel at the impossible beauty of it all. This has been Animal Uncovered. Until next time, may you carry with you the wonder of the octopus, a reminder that intelligence takes many forms, consciousness burns in many ways, and in the vast ocean of existence, every life, however brief, has the potential for genius. That extraordinary sound is the voice of one of nature's most remarkable timekeepers. For decades they have waited in darkness. Now, driven by an ancient biological clock more precise than any human chronometer, millions upon millions of creatures are about to emerge from their underground cathedral and transform the very air above us into a symphony of desire. Welcome to Animal Uncovered. I'm your host, and today we explore the insane life cycle of cicadas. Picture, if you will, a forest floor in the eastern United States. To the casual observer, nothing seems amiss. Children play beneath oak trees, joggers follow familiar paths. But beneath their feet, Just 18 inches below the surface, something extraordinary is stirring. The soil temperature has reached precisely 64 degrees Fahrenheit, 18 degrees Celsius. This is the signal they have been waiting for. After 17 long years of patient existence in the Earth's embrace, the nymphs of Magicicada septendecim begin their ascent. According to research published by the Smithsonian Institution's National Museum of Natural History, these creatures possess what may be the longest developmental period of any insect on Earth: 17 years. To put this in perspective, a cicada nymph that began its journey when you were born is only now reaching maturity as you listen to these words. The emergence begins at dusk when the air cools and the light softens. Tiny, ghost-pale creatures, no larger than your thumb, push through the earth with claws perfectly designed for digging. Their eyes, large and bulbous, see the world above for the first time since they fell from the trees as helpless eggs nearly 2 decades ago. But they are not alone. Oh no, they are never alone. The USDA Forest Service has documented emergence densities of up to 1.5 million cicadas per acre. Imagine that. In a single acre of woodland, roughly the size of a football field, 1.5 million creatures are simultaneously clawing their way to the surface. The ground literally writhes with their movement. They move with purpose, these ancient mariners of the soil. Each nymph seeks the perfect launching pad, the trunk of a tree, a fence post, a garden wall. Anything vertical will do. For what comes next is perhaps the most vulnerable moment in their extraordinary lives. The process is called ecdysis, the molting of their nymphal skin. Like a performer shedding a costume, each cicada must emerge from the only body it has ever known. First, a split appears along the back, then slowly, impossibly, the adult cicada begins to pull itself free. The transformation is mesmerizing. Where once there was a pale, earth-dwelling creature with stubby wing pads, now emerges an insect of surprising beauty. Wings transparent as stained glass windows, eyes like polished amber, and a body that gleams with iridescent green and black. But they are soft now, vulnerable. For the next few hours their exoskeleton must harden. Their wings must expand and strengthen. They are defenseless, relying entirely on synchronicity and overwhelming numbers for survival. This is the genius of their strategy. By emerging together, by presenting predators with more food than could possibly be consumed, most will survive to fulfill their ancient purpose. But why 17 years? Why not 15 or 20 or some other arbitrary number? The answer lies in one of nature's most elegant mathematical solutions to the problem of survival. Dr. Mario Marcus of the Max Planck Institute has studied the evolutionary mathematics behind cicada emergence cycles. The numbers 13 and 17, the two primary cycles of North American periodical cicadas, are both prime numbers. This is no coincidence. Imagine for a moment that you are a predator whose own life cycle follows a predictable pattern. Perhaps you reproduce every 2 years, or every 4 years. If cicadas emerged every 12 years, you might sync up with them every 4th generation, or every 3rd, but 17. The mathematics make synchronization nearly impossible. A predator with a 2-year cycle would only align with the cicadas once every 34 years. A 4-year cycle, once every 68 years. By the time any predator population could adapt to predict their emergence, the advantage would be lost in the vast sweep of evolutionary time. The journal Ecology published research demonstrating that this prime number strategy reduces predation pressure by up to 90% compared to shorter, non-prime cycles. It is, quite literally, a numbers game written in the language of natural selection. But there's more to their survival strategy than mere mathematics. The sheer volume of their emergence creates what scientists call predator satiation. Research from the Smithsonian Environmental Research Center shows that during peak emergence years, local bird populations consume only about 15% of available cicadas, despite eating virtually nothing else during the emergence period. The forest becomes a buffet so vast that even the most voracious predators cannot make a meaningful dent in their numbers. Raccoons gorge themselves until they can barely move. Birds feed their young exclusively on cicadas for weeks. Even family pets grow fat on the windfall. Yet for every 1,000 cicadas consumed, tens of thousands more survive to mate and perpetuate the cycle. Now, you might wonder, how do creatures that spend 99% of their lives underground coordinate such precisely timed mass emergences? The answer lies in their extraordinary ability to count. Not count in the way we might count, but to track the passage of seasons with remarkable precision. Deep in the soil, cicada nymphs monitor the chemical changes in tree roots as sap flows, and nutrients shift with each passing spring and autumn. University of Connecticut researcher Dr. Chris Simon has spent decades studying this phenomenon. Her research, published in Evolution, suggests that cicadas essentially count the number of seasonal cycles they experience through changes in amino acid concentrations in tree root fluids. It's as though each cicada carries within its primitive brain a biological calendar, marking off the years with chemical precision until that magical moment when the count reaches 17, the soil temperature hits 64 degrees, and the great emergence begins. Most people are familiar to the sound cicadas make. To human ears, it might seem like mechanical noise, the sound of summer itself. But to a female cicada, each note carries the promise of genetic legacy. The male cicada's song is produced by a remarkable instrument called a timbal, a ribbed membrane on either side of his abdomen. By rapidly flexing these timbals, he creates sound pulses that can reach 120 decibels. That's louder than a chainsaw, louder than a rock concert, approaching the threshold of human pain. But volume is only part of the story. Each species of cicada has its own distinct song, as unique as a human fingerprint. Magicicada cassini produces a steady drone. Magicicada septendecula creates a rapid ticking sound like bacon frying in oil. Magicicada septendecim offers a complex phrase that rises and falls like a question being asked. Research published in the journal Animal Behavior reveals that these songs serve multiple purposes. They announce the male's location, advertise his fitness, and create what acoustics experts call acoustic space, invisible territories marked by sound rather than scent or visual displays. But perhaps most remarkably, when thousands of males sing together, they create something unexpected. Silence. Not actual silence, of course, but acoustic windows. Brief moments when all the males pause simultaneously, allowing them to hear the subtle wing flick responses of interested females. Dr. John Cooley of the University of Connecticut has documented this behavior extensively. Males will sing for several seconds, then pause as if listening. During these quiet moments, females respond with rapid wing movements that create a sharp clicking sound. It's a conversation conducted entirely in rhythm and timing. The mating process itself is remarkably brief. After all those years of waiting, the actual act of reproduction takes mere minutes. But what follows is perhaps the most touching aspect of their entire life cycle. Unlike many insects that mate and immediately move on, cicadas often remain together for hours or even days. They seem to savour these final moments of their above-ground existence, as if aware that their time in the sun is rapidly drawing to a close. The females have one final task. Using their sword-like ovipositor, they cut precise slits in young tree branches and deposit their eggs, sometimes up to 600 per female. It's exhausting work that requires perfect timing. The branches must be young enough to penetrate but mature enough to support the developing eggs. Each egg slit weakens the branch slightly. When thousands of females work the same tree, the cumulative damage causes what arborists call flagging, the browning and death of branch tips. It looks devastating, but research from the USDA Forest Service confirms that this pruning actually stimulates new growth, making the forest healthier in the long term. And then, as suddenly as it began, it ends. Within 4 to 6 weeks of emergence, the adult cicadas begin to die. Not from predation, not from disease, but from the simple completion of their biological purpose. Their bodies, designed for reproduction rather than longevity, simply shut down. The forest floor becomes carpeted with their remains. It might seem tragic, this mass dying after such a brief moment in the sun. But death, for cicadas, is not an ending. It's an investment in the future. Research published in the journal Oecologia by Dr. Louis Yang at UC Davis demonstrates that cicada carcasses provide a massive pulse of nutrients to forest ecosystems. A single emergence can deposit over 200 pounds of protein and other nutrients per acre, the equivalent of adding high-quality fertilizer to the entire forest floor. The trees that will shelter the next generation grow stronger because of these deaths. Small mammals that gorge themselves during the emergence produce larger, healthier litters. Even soil microorganisms benefit from the bounty, creating cascading effects that ripple through the ecosystem for years. But the story doesn't end with the adults. Deep in the tree branches, protected within their mother's carefully carved slits, the eggs are developing. In 6 to 8 weeks, they will hatch into tiny nymphs no larger than rice grains. Gravity is their guide as they drop from the branches to the forest floor. They have no wings, no ability to steer their descent. It's pure chance whether they land on suitable soil or on concrete, on rich earth or barren rock. Many will perish in this lottery of location, but those that find the right spot will dig. With claws perfectly designed for the task, they will burrow down through leaf litter, through topsoil, down to where the tree roots grow thick and strong. There, in darkness absolute, they will begin the long wait. For the next 17 years they will live as miners in the earth, tapping into tree roots like tiny vampires. They will molt 5 times, growing slowly, incrementally, adding mass grain by grain. They will survive droughts that kill surface vegetation, floods that would drown air-breathing creatures, and winters that freeze the soil solid. They are perhaps the most patient creatures on Earth, these cicadas. While entire human generations are born, grow up, and pass away, they wait in darkness, counting seasons, measuring time in ways we can barely comprehend. The nymphs that are burrowing into the soil as I speak will emerge in the year 2042. The children who hear their songs then may well have children of their own. It's a perspective that puts our brief human concerns into cosmic context. Standing in a forest during a cicada emergence, surrounded by millions of creatures completing a journey that began before you were born, one cannot help but feel humbled by the vast scales of natural time. These insects embody patience in its purest form. They represent the power of synchronicity, the mathematics of survival, and the profound beauty of living systems that operate on timescales far beyond human experience. In our fast-paced world of instant communication, An immediate gratification, cicadas remind us that some of nature's greatest achievements require not speed, but persistence, not innovation, but faithfulness to ancient patterns. The next major emergence of 17-year cicadas in the eastern United States will occur in 2038. Mark your calendars. Set a reminder. For when that time comes, you will witness one of the natural world's most extraordinary spectacles. Millions of creatures completing a journey they began in darkness, decades ago, driven by an inner clock more reliable than any human timepiece. Until then, they wait, patient as stone, faithful as sunrise, counting the seasons in their dark cathedral beneath our feet. This has been Animal Uncovered, reminding you that in nature, timing is everything. In the perpetual darkness of Earth's final frontier, where sunlight has never touched and pressure would crush the human body in an instant, there exists a realm so alien that it might as well be on another planet entirely. Here, in the deepest reaches of our oceans, dwells a creature whose very existence challenges our understanding of life, love, and the extraordinary lengths to which evolution will go to ensure survival. This is the story of the anglerfish, a being so bizarre, so perfectly adapted to its hellish environment, that nature herself seems to have crafted it from the stuff of nightmares and dreams in equal measure. It is a tale of sexual parasitism so extreme that it defies comprehension, of predatory cunning that would make Machiavelli himself blush, and of evolutionary trade-offs so profound that they rewrite the very rules of what it means to be alive. Welcome to Animal Uncovered. I'm your host, taking you on a journey to the very bottom of the world, where the strange and the beautiful dance together in eternal darkness, and where one of nature's most extraordinary life cycles unfolds in the crushing depths of the abyss. Chapter 1. Into the Abyss. Picture, if you will, descending through layers of ocean that grow progressively darker, colder, and more alien with each passing meter. At 200 meters below the surface, the last traces of sunlight fade into memory. At 1,000 meters, we enter what marine biologists call the bathypelagic zone, the midnight zone, where eternal darkness reigns supreme and the pressure reaches 100 times that of the surface. Here, in this vast underwater desert, water temperatures hover just above freezing. The pressure is so immense, over 1,400 pounds per square inch, that it would instantly collapse a human lung. Yet it is in this seemingly impossible environment that the anglerfish has not merely survived, but thrived for millions of years. The deep sea is Earth's largest habitat, covering more than 90% of the living space on our planet, yet it remains more mysterious to us than the surface of Mars. Recent research suggests that anglerfish suborders most likely diverged from one another during the late Cretaceous and Paleocene periods, making them ancient mariners of the deep, witnesses to the rise and fall of entire geological ages. In this realm of perpetual midnight, the rules of existence are rewritten entirely. Food is scarce, so scarce that when a meal presents itself, it cannot be allowed to escape. Energy conservation becomes not just advantageous, but absolutely critical for survival. Every calorie burned must be justified, every movement calculated with the precision of a master chess player contemplating their next move. It is here, in this most inhospitable of environments, that evolution has crafted perhaps its most ingenious and disturbing reproductive strategy, one that transforms the very concept of romantic partnership into something that would be unrecognizable to any surface dweller. Chapter 2. The Living Lure. In the absolute darkness of the deep sea, light becomes currency, the most valuable commodity in an economy of survival. And the anglerfish, with evolutionary cunning that borders on genius, has learned to mint its own. Suspended from the anglerfish's head like a macabre fishing rod is one of nature's most sophisticated hunting tools, the Elysium, topped with its glowing esque, a biological lure that pulses with an otherworldly blue-green light. This is not merely bioluminescence. This is biological warfare conducted at the molecular level. The light emanates not from the anglerfish itself, but from symbiotic bacteria that have formed one of the ocean's most remarkable partnerships. These microscopic allies, acquired from the environment rather than inherited, have undergone such extensive genetic reduction that they can no longer survive independently. They have become living light bulbs, their entire existence devoted to producing the ethereal glow that will spell doom for countless unsuspecting victims. This borrowed bioluminescence represents a creative evolutionary workaround that transforms the anglerfish from a sluggish deep-sea dweller into one of the ocean's most efficient predators. The bacteria within the esker produce light through a chemical reaction involving luciferin and luciferase, the same process that creates Firefly's summer evening dance, but here repurposed for a far more sinister ballet. The anglerfish positions itself in the water column with the patience of a monk in meditation, its massive mouth agape, revealing rows of needle-sharp teeth that curve inward like the bars of a living prison. The lure dances hypnotically in the water, mimicking the movement of small prey. A wounded fish, perhaps, or a succulent copepod drifting helplessly in the current. To the hungry eyes of deep-sea creatures, fish that may not have eaten in weeks or even months, this glowing morsel appears to be salvation itself. They approach with desperate hunger, drawn by instincts honed over millions of years of evolution, never suspecting that they are swimming toward their doom. When prey ventures within striking distance, the anglerfish's response is instantaneous and devastating. Its jaw mechanism can extend forward with explosive speed, creating a suction so powerful that it literally vacuums the victim into its cavernous mouth. The entire process takes mere milliseconds, faster than the human eye can follow, faster than the prey can react. With its bucket-sized mouth bearing razor-sharp teeth and tiny frosted eyes, the anglerfish has evolved into a living bear trap, perfectly calibrated for its harsh environment. Those inward curving teeth ensure that nothing once caught can ever escape. The prey is swallowed whole, often still alive, to be dissolved slowly by powerful digestive enzymes in the anglerfish's expandable stomach. This hunting strategy represents one of evolution's most elegant solutions to the problem of energy scarcity in the deep sea. Rather than expending precious calories in pursuit of prey, the anglerfish has become a living mousetrap, allowing its victims to come to it. In an environment where a single missed meal might mean the difference between life and death, such efficiency is not merely advantageous, it is essential for survival. Chapter 3. The Great Divide. But it is in the realm of reproduction that the anglerfish reveals its most astonishing adaptations, beginning with a sexual dimorphism so extreme that early marine biologists believed they were observing entirely different species. The female anglerfish is a formidable creature, an apex predator that can grow to lengths of more than 3 feet and weigh several pounds. She is the embodiment of deep-sea power, equipped with that devastating lure, expandable jaws, and a digestive system capable of processing prey larger than herself. She's perfectly adapted for hunting, for survival, for the endless battle against starvation that defines life in the abyss. The male, by contrast, appears to belong to an entirely different evolutionary strategy. Males are often 10 times smaller than females and have no function other than to reproduce. While the female grows into a fearsome predator, the male remains diminutive, sometimes no larger than a human thumb, with a body plan that seems almost rudimentary by comparison. This extraordinary size difference is not merely unusual, it represents one of the most extreme examples of sexual dimorphism in the animal kingdom. To put this in perspective, imagine if human males averaged 6 inches in height, while females grew to 60 feet. Such is the scale of difference we observe in certain anglerfish species. The male's entire anatomy reflects a life dedicated to a single, overwhelming purpose: finding and fertilizing a female. His eyes, proportionally much larger than the female's, are optimized for detecting the faint bioluminescent signals that might indicate a female's presence in the vast darkness. They possess highly developed scent organs to track down females, allowing them to detect and follow chemical trails across miles of open ocean. Unlike his mate, the male anglerfish lacks the sophisticated hunting apparatus that makes the female such an effective predator. He has no lure, no expandable jaws, no ability to capture large prey. His mouth is small, his teeth weak, his entire body streamlined not for hunting, but for one epic journey across the dark expanse of the deep sea. This sexual dimorphism reflects one of evolution's most fundamental trade-offs. In an environment where resources are scarce and finding a mate is extraordinarily difficult, natural selection has favoured a strategy where one sex, the female, specialises in survival and growth, while the other, the male, specialises entirely in reproduction. The female becomes a living fortress, capable of surviving for years in the harsh deep-sea environment. The male becomes a guided missile, programmed with a single mission: find a female and ensure the continuation of his genetic line. This division of evolutionary labour sets the stage for one of the most bizarre and disturbing mating rituals in the natural world, a process so extreme that it challenges our very understanding of what it means to be an individual organism. Chapter 4: The Ultimate Commitment. In the perpetual darkness of the deep sea, finding a mate is not merely difficult, it is nearly impossible. Imagine trying to locate a single specific person in a space the size of North America in complete darkness, with no roads, no landmarks, and no means of communication beyond chemical signals that disperse randomly in 3-dimensional space. This is the challenge that faces every male anglerfish as he reaches sexual maturity. These deep-sea anglerfishes, called ceratioids, reproduce through sexual parasitism, in which the tiny males attach to their much larger female counterparts to mate. But the term sexual parasitism barely begins to capture the profound biological transformation that unfolds when male meets female in the abyss. The male's journey begins with an epic migration through the darkness, following chemical gradients so faint that they exist at the very limits of biological detection. He may travel for days, weeks, or even months, navigating by scent alone through a 3-dimensional maze of ocean currents and thermal layers. His body burns through its limited energy reserves, driven by instincts so powerful that they override even the most basic drive for self-preservation. When at last he detects the telltale chemical signature of a female, the male's behavior becomes increasingly frenzied. He follows the scent trail with single-minded determination, his proportionally enormous eyes scanning the darkness for any sign of the massive predator he seeks to join. The irony is profound. He is simultaneously hunting for and being hunted by the same creature, for if he approaches incorrectly, he may well end up as her next meal rather than her mate. In some species, the males bite the females and then release once the mating process is complete. But in others, something far more extraordinary occurs, something that transforms the very meaning of biological partnership. When the male locates a suitable female, he positions himself near her body and bites down with specialized teeth that have evolved specifically for this moment. But this is no ordinary bite. As his teeth penetrate her skin, a cascade of biological processes begins that will forever alter both of their lives. The male's jaw begins to fuse with the female's flesh. His circulatory system merges with hers. His organs begin to atrophy, becoming vestigial remnants of their former selves. Over the course of days or weeks, the male essentially dissolves into the female, becoming nothing more than a living sperm-producing appendage attached to her body. This unusual phenomenon of sexual parasitism involves the permanent attachment of dwarf males to much larger females and fusion of their tissues, leading to the establishment of a shared circulatory system. The male's kidneys shut down. He no longer needs them, as the female's circulatory system now handles waste processing for both organisms. His digestive system atrophies. The female will provide all necessary nutrients through her bloodstream. His brain shrinks to a fraction of its original size, retaining only the neural pathways necessary to produce sperm when hormonally triggered. What emerges from this process is a creature that challenges our fundamental understanding of individuality. Is this still two organisms, or has it become one? The male retains his own genetic identity, yet he has no independent existence. He has willingly sacrificed his autonomy, his mobility, his very selfhood, for the chance to ensure his genetic legacy. From the female's perspective, she's acquired what amounts to a permanent sperm bank, a ready source of genetic material that she can access whenever conditions are favourable for reproduction. She no longer needs to expend energy searching for mates or risk the dangers of courtship in the deep sea. Her parasitic partner is always available, always ready to fulfill his biological function. This extraordinary arrangement represents evolution's solution to one of the most challenging reproductive puzzles in the natural world. In an environment where encounters between potential mates are so rare that they might happen only once in a lifetime, sexual parasitism ensures that when such meetings do occur, they result in permanent reproductive partnerships that can last for years or even decades. Chapter 5. A Living Contradiction. The fusion of male and female anglerfish creates a biological entity that seems to exist in defiance of nature's usual rules. Here is a creature that's simultaneously predator and parasite, individual and collective, autonomous and dependent. The merged organism embodies contradictions that illuminate the profound flexibility of evolutionary processes. Even though they form these tight bonds during mating, reproduction occurs via external fertilization, when environmental conditions signal that the time is right, perhaps when food becomes abundant, or when chemical cues indicate the presence of optimal spawning conditions. The female's body begins producing hormones that trigger reproductive readiness in both partners. The female's ovaries swell with thousands of eggs, each one a potential future anglerfish carrying the genetic legacy of both partners. Meanwhile, the parasitic male, responding to the same hormonal signals coursing through their shared bloodstream, begins producing vast quantities of sperm. Despite his diminished physical form, his reproductive organs remain fully functional, ready to fulfill the purpose for which he has sacrificed everything else. When the moment arrives, the female releases her eggs into the dark water column in a spectacular display of reproductive optimism. Thousands upon thousands of tiny spheres drift away from her body, each one carrying the potential for new life. The parasitic male simultaneously releases clouds of sperm, which seek out and fertilize the eggs in the surrounding water. This external fertilization strategy might seem paradoxical. Why maintain such an intimate physical connection, only to reproduce at a distance? The answer lies in the economics of deep-sea survival. By keeping the male permanently attached, the female ensures that sperm will always be available when conditions are optimal for reproduction. Yet by releasing eggs and sperm into the water column, she maximizes the dispersal of her offspring, giving them the best possible chance of finding suitable habitat in the vast emptiness of the deep sea. The fertilized eggs begin their own epic journey, drifting through layers of ocean that represent entirely different worlds. As they develop, the tiny embryos face challenges that would defeat most life forms. They must survive in water so cold it would freeze the blood of surface-dwelling creatures. They must develop in darkness so complete that the concept of vision becomes almost meaningless. They must grow in an environment where food is scarce and predators are abundant. Yet somehow, through mechanisms that still puzzle marine biologists, a tiny percentage of these embryos survive to become larvae, then juveniles, then adults capable of continuing this extraordinary cycle. Each successful reproduction represents a victory against odds so astronomical that they border on the miraculous. The adult female, her reproductive duty temporarily fulfilled, returns to her patient hunting. Her parasitic mate, having served his biological function, settles back into his diminished existence, alive yet not truly living, individual yet not truly independent. He will remain with her for the rest of their lives, a living testament to evolution's ability to push the boundaries of biological possibility. Some females collect multiple males throughout their lives, creating bizarre biological harems where several parasitic partners attach to different parts of her body. These polyandrous arrangements further increase reproductive success while creating creatures that seem more like something from science fiction than from the natural world. Chapter 6. The Price of Survival. The anglerfish's reproductive strategy represents one of evolution's most extreme examples of biological specialization. But like all evolutionary adaptations, it comes with profound costs that illuminate the fundamental trade-offs inherent in the struggle for survival. Consider the male's sacrifice, complete autonomy traded for reproductive certainty. In most animal species, males retain their independence even after mating, free to seek additional partners, to compete for territory, to live lives of their own choosing. The male anglerfish abandons all of this, becoming what is essentially a living organ attached to his mate's body. His consciousness, if such a thing can be said to exist in fish, becomes subsumed into a larger biological entity over which he has no control. From an evolutionary perspective, this sacrifice makes perfect sense. In the deep sea, the chances of a free-living male finding a second mate are essentially zero. By fusing permanently with the first female he encounters, he guarantees that his genes will be passed on, which is evolution's ultimate measure of success. Yet from the perspective of individual experience, the transformation represents a kind of living death, the cessation of independent existence in service of genetic immortality. The female too pays costs for this arrangement, though they are more subtle. Sexual parasitism enables anglerfishes to maximize reproductive success, but it also commits her to supporting additional biological mass that provides no immediate survival benefit. The parasitic male must be fed, his tissues maintained, his metabolic needs met, all of which represent energy that could otherwise be devoted to growth, hunting, or survival. Moreover, the permanent attachment of males makes the female a more conspicuous target for predators. A solitary female anglerfish presents a relatively streamlined profile in the water. A female with multiple parasitic males attached becomes a more ungainly creature, potentially less maneuverable, and more likely to be detected by the few predators capable of threatening an adult anglerfish. These trade-offs extend beyond the individual to shape the entire ecosystem of the deep sea. Key adaptations such as rapid diversification, larger jaws, smaller eyes, and more diverse body shapes facilitated the transition of anglerfishes from benthic to pelagic environments. The evolution of sexual parasitism has allowed anglerfishes to colonize ecological niches that would otherwise be inaccessible, spreading throughout the world's oceans and diversifying into more than 160 different species. Yet this success comes at the cost of biological flexibility. Once committed to the path of sexual parasitism, anglerfish species become locked into this reproductive strategy. They cannot easily evolve back to more conventional mating systems, even if environmental conditions change in ways that might favour such a shift. Evolution has painted them into a corner of biological specialisation from which there may be no escape. The implications extend population genetics as well. In most animal species, genetic diversity is maintained through the mixing of genes from multiple partners over multiple generations. But in anglerfishes with permanent sexual parasitism, each female typically reproduces with the same male or small group of males throughout her entire life. This reduces genetic mixing and could potentially make populations more vulnerable to disease or environmental change. Despite these costs, the anglerfish's reproductive strategy has proven remarkably successful over geological timescales. The multiple families of deep-sea anglerfishes, as well as their trademark sexual parasitism, originated during the Eocene in a rapid radiation that filled ecological niches throughout the world's oceans. Their success demonstrates that in extreme environments, extreme adaptations may be not just advantageous, but necessary for survival. The anglerfish thus serves as a living reminder that evolution does not optimize for human concepts of dignity, independence, or individual fulfillment. It optimizes only for the successful transmission of genetic material to the next generation, and it will employ whatever strategies, no matter how bizarre or disturbing, necessary to achieve that goal. Chapter 7: Diversity in the Darkness. The deep sea is not a uniform environment, and the anglerfishes that inhabit it have evolved a spectacular array of variations on their basic theme of sexual parasitism. From the crushing depths of oceanic trenches to the relatively shallow waters of the continental slope, different species have refined this reproductive strategy in ways that reflect the subtle but crucial differences in their environments. In other anglerfishes, the male is closer in size to the female, and only encounters her to mate, spending the rest of their lives hunting for themselves and swimming freely in the ocean. These species represent evolutionary experiments in reproductive strategy, some maintaining traditional courtship and mating systems, while others push the boundaries of sexual parasitism to ever greater extremes. Recent research has revealed that the diversity of anglerfish species is far greater than previously imagined, with new species being discovered regularly as deep-sea exploration technology advances. Each species represents a unique solution to the fundamental challenges of deep-sea existence, with variations in body size, lure structure, reproductive strategy, and ecological niche that demonstrate evolution's remarkable creativity. Some species have evolved lures that pulse with different rhythms, creating species-specific signals that help ensure mating occurs between compatible partners. Others have developed multiple lures or lures with complex branching structures that may attract different types of prey. Recent discoveries have even documented biofluorescence in deep-sea anglerfishes, adding yet another layer of complexity to their already sophisticated light-based communication and hunting systems. The geographic distribution of anglerfish species provides insights into the history of ocean basins and the processes that drive speciation in the deep sea. Some species are found throughout the world's oceans, suggesting either recent global dispersal or ancient evolutionary origins that predate the current configuration of ocean basins. Others are restricted to specific regions, indicating more recent evolutionary divergence or adaptation to local environmental conditions. These patterns of diversity and distribution remind us that the deep sea, despite its apparent uniformity, contains a multitude of microenvironments that can drive evolutionary divergence. Temperature gradients, current patterns, food availability, and chemical composition all vary across the ocean basins, creating selective pressures that shape the evolution of local populations and eventually lead to the formation of new species. The study of anglerfish diversity also illuminates broader patterns of evolution in extreme environments. The deep sea shares certain characteristics with other extreme habitats. Antarctica, high-altitude mountains, deep underground caves, where life faces similar challenges of resource scarcity, environmental extremes, and isolation. In each of these environments, evolution has favoured similar strategies: energy conservation, specialised feeding mechanisms, and reproductive adaptations that maximise the chances of successful mating, despite sparse population densities. Chapter 8: Windows into Evolution. The anglerfish's extraordinary adaptations offer profound insights into the fundamental processes that drive evolutionary change. Their sexual parasitism represents an extreme example of how environmental pressures can push life forms towards solutions that seem to violate basic biological principles, yet prove remarkably effective in their specific ecological contexts. The evolution of sexual parasitism in anglerfishes illuminates several key evolutionary concepts. First, it demonstrates how extreme environmental constraints can favour equally extreme adaptations. The deep sea's combination of darkness, sparse food, and low population density creates conditions where conventional reproductive strategies become ineffective, opening evolutionary pathways toward more radical solutions. Second, the anglerfish story illustrates the concept of evolutionary trade-offs with exceptional clarity. Every adaptation carries costs as well as benefits, and evolution proceeds by balancing these trade-offs in ways that maximize overall reproductive success. The male anglerfish's sacrifice of independence for reproductive certainty represents perhaps the most extreme example of such a trade-off in the animal kingdom. Third, anglerfish evolution demonstrates how seemingly impossible biological transitions can occur through gradual steps. The transition from conventional mating to full sexual parasitism likely occurred through intermediate stages, perhaps beginning with males that simply remained near females for extended periods, then evolving temporary attachment mechanisms, and finally developing permanent fusion capabilities. Each step in this progression would have been favoured by natural selection under deep-sea conditions, leading eventually to the extraordinary reproductive strategy we observe today. The molecular mechanisms underlying sexual parasitism are beginning to yield to scientific investigation, revealing the genetic and biochemical processes that make such extreme biological integration possible. The establishment of a shared circulatory system between male and female represents a remarkable feat of biological engineering that requires precise regulation of immune responses, tissue compatibility, and physiological integration. Understanding these mechanisms has implications that extend far beyond marine biology. The ability of male and female anglerfishes to merge their circulatory systems without triggering lethal immune responses could provide insights into tissue compatibility and organ transplantation in humans. The process of controlled tissue fusion might inform research into regenerative medicine and tissue engineering. Moreover, the anglerfish's reproductive strategy serves as a natural experiment in the evolution of cooperation and conflict between the sexes. In most animal species, males and females have partially conflicting evolutionary interests. Each individual seeks to maximize their own reproductive success, which may come at the expense of their partner's success. But in anglerfishes with permanent sexual parasitism, these conflicts are essentially resolved through the complete subordination of male interests to female interests. This resolution of sexual conflict through extreme specialization offers insights into the evolutionary dynamics of cooperation more generally. It suggests that under certain conditions, evolution can favor the complete sacrifice of individual interests in service of collective success, a principle that may apply to other forms of biological cooperation, from the evolution of multicellularity to the organization of social insect colonies. Chapter 9: Challenges in the Abyss. Life in the deep sea presents challenges so severe that they push biological systems to their absolute limits. For anglerfishes, every aspect of their existence reflects adaptations to an environment that seems fundamentally hostile to life as we understand it. The pressure at anglerfish depths, often exceeding 100 times atmospheric pressure, requires specialized adaptations in every organ system. Proteins must be modified to function under these extreme conditions, maintaining their structure and function despite forces that would denature most biological molecules. Gas-filled organs like swim bladders must be modified or eliminated entirely, as they would collapse instantly under such pressure. Temperature presents another formidable challenge. The deep sea maintains temperatures just above freezing year-round, requiring specialized enzymes and metabolic pathways that can function efficiently in extreme cold. Cellular membranes must be modified to remain flexible despite the low temperatures, using specialized lipids that resist freezing. Perhaps most challenging of all is the scarcity of food in the deep sea. Primary productivity, the conversion of inorganic compounds into organic matter, is virtually non-existent in the darkness of the abyss. All energy must ultimately derive from the surface waters, either through the slow rain of dead organic matter that drifts down from above, or through the occasional carcass of a large animal that sinks to the seafloor. This energy scarcity shapes every aspect of anglerfish biology. Their hunting strategy of passive ambush predation minimizes energy expenditure while maximizing the chances of capturing rare prey items. Their slow metabolic rate allows them to survive for months between meals. Their reproductive strategy ensures that when mating opportunities arise, they result in permanent partnerships that eliminate the need for repeated mate searching. The darkness of the deep sea eliminates the possibility of photosynthesis and makes vision nearly useless for most purposes. Yet anglerfishes have turned this challenge into an opportunity, evolving sophisticated bioluminescent systems that function as both hunting tools and communication devices. The symbiotic relationship between anglerfishes and their luminous bacteria represents one of nature's most elegant solutions to the problem of producing light in a lightless world. Chemical challenges abound as well. The deep sea has different oxygen levels than surface waters, requiring specialized respiratory adaptations. The high pressure affects the solubility of gases in body fluids, potentially creating problems with gas bubble formation similar to decompression sickness in human divers. Heavy metals and other chemical compounds may be present in concentrations that would be toxic to surface-dwelling organisms. Despite these formidable challenges, anglerfishes have not merely survived in the deep sea, they have flourished, diversifying into a remarkable array of species that occupy virtually every available ecological niche in the abyss. Their success demonstrates the extraordinary power of evolutionary adaptation to overcome even the most extreme environmental challenges. The study of how anglerfishes cope with deep-sea conditions continues to yield insights that may prove valuable for human technology. Their pressure-resistant proteins could inform the development of materials for deep-sea exploration equipment. Their efficient bioluminescent systems could inspire new approaches to lighting and display technology. Their methods of energy conservation could suggest strategies for designing more efficient machines and systems. Chapter 10: The Eternal Dance. In the perpetual midnight of the deep sea, the anglerfishes continue their ancient dance of survival and reproduction, a ballet that has been performed for millions of years in the crushing darkness of the abyss. Theirs is a story that transcends mere biology, touching on fundamental questions about the nature of existence, sacrifice, and the price of survival in an unforgiving world. Each female anglerfish that glides through the darkness carries with her the accumulated wisdom of countless generations, genetic instructions refined by millions of years of natural selection, behavioral patterns honed by the relentless pressure of survival in the world's most challenging environment. Her glowing lure pulses with ancient rhythms, following patterns that have proved their worth over geological ages. Somewhere in the vast darkness, a male responds to chemical signals so faint they exist at the very threshold of detection. His journey toward her represents both a pilgrimage and a suicide mission, a final act of devotion that will transform him from an independent being into a living component of a larger biological entity. In human terms, his fate seems tragic, even horrifying. In evolutionary terms, it represents the ultimate success, the guarantee that his genetic legacy will survive and flourish. The fusion of male and female creates something unprecedented in the natural world, a creature that challenges our fundamental understanding of individuality and autonomy. The merged organism that results embodies contradictions that illuminate the profound flexibility of life itself. It is simultaneously one creature and two, predator and parasite, ancient and eternally renewable. When the time comes for reproduction, the female releases her eggs into the water column with an act of faith that spans generations. Each egg represents a potential future, a genetic lottery ticket that might, against overwhelming odds, develop into an adult capable of continuing this extraordinary cycle. The vast majority will perish, consumed by predators or claimed by the hostile environment. But a precious few will survive, carrying forward the genetic instructions that have made anglerfishes among the most successful inhabitants of the deep sea. The larvae that emerge from these surviving eggs begin their own epic journeys through the layered waters of the ocean. They must navigate through different water masses, each with its own temperature, salinity, and chemical composition. They must find food in an environment where sustenance is scarce and competition is fierce. They must avoid predators while growing large enough to become predators themselves. Those that survive to adulthood will eventually face the same choices that have confronted their ancestors for millions of years. The females will develop their lures, establish their territories, and wait with infinite patience for prey to venture within range. The males will embark on their desperate searches for mates, driven by instincts so powerful that they override even the most basic drive for self-preservation. And so the cycle continues, an eternal repetition of themes that speak to the deepest mysteries of existence. In the crushing darkness of the deep sea, life persists not through comfort or ease, but through adaptations so extreme that they seem to mock our conventional understanding of biological possibility. Thank you for joining us on this journey to the bottom of the world, where the impossible becomes possible, and where creatures like the anglerfish continue to illuminate the darkness with their ancient wisdom and their eternal light. In the floating gardens of an ancient lake, where the last remnants of an Aztec empire once flourished, there exists a creature so extraordinary that it appears to have struck a bargain with time itself. While the world around it rushes toward maturity, toward the inevitable march of aging and decay, this remarkable being has chosen a different path entirely. It has decided, quite simply, never to grow up. The axolotl, Ambystoma mexicanum, its very name whispers of mythology, from the Nahuatl atl meaning water, and Xolotl, the Aztec god of lightning and death who, according to legend, transformed himself into this creature to avoid being sacrificed. How fitting, then, that this animal should embody its own form of immortality. Welcome to Animal Uncovered. I'm your host, and today we journey into one of nature's most profound mysteries, a life cycle so unusual, so utterly contrary to everything we understand about growth and development, that it challenges our very conception of what it means to mature, to age, to become complete. Part 1. The Peter Pan Paradox. Picture, if you will, a world where childhood never ends, where the playground of youth stretches not for years, but for an entire lifetime. This is the reality of the axolotl, a creature that has mastered perhaps the most enviable trait in all of nature, eternal youth. But this is not the superficial youth that humans chase with potions and procedures. This is neoteny, the retention of juvenile characteristics throughout adult life. The axolotl has taken this evolutionary strategy to its absolute extreme, becoming sexually mature while maintaining the body of a larva, the gills of a tadpole, the wonder of perpetual childhood. In the murky waters of their ancestral home, Lake Xochimilco, these creatures glide through their aquatic world with an otherworldly grace. Their external gills, 3 feathery plumes on each side of their head, wave like delicate coral fans, filtering oxygen from the water with the same efficiency they possessed as true juveniles. These gills, which in almost every other amphibian would be absorbed and replaced by lungs, here remain as permanent fixtures, a testament to nature's ability to pause, to hold a moment in time and make it eternal. The axolotl's skin remains permeable, thin and delicate, never developing the thick protective hide of terrestrial adult amphibians. Their limbs stay slender and graceful, never gaining the robust musculature needed for life on land. Their skull remains cartilaginous in places where bone should have formed, maintaining a juvenility that extends to their very skeleton. Yet within this perpetually youthful body, the reproductive organs mature fully. By 8 to 12 months, these eternal children are capable of creating new life, of passing on their extraordinary gift to the next generation. They court and mate while looking for all the world like the tadpoles they once were and in many ways still are. This is evolution's greatest magic trick, the ability to separate physical development from reproductive maturity, to cherry-pick the benefits of youth, while embracing the responsibilities of adulthood. The axolotl has found a way to have its cake and eat it too, to remain forever young while ensuring its species' continuation. Part 2. The Miracle of Regeneration. But if eternal youth were the axolotl's only extraordinary gift, it would already rank among nature's most remarkable creatures. Yet this aquatic marvel possesses another ability so profound, so seemingly impossible, that it reads like science fiction, the power of regeneration. When an axolotl loses a limb, whether to predation, accident, or the casual violence of nature, it does not simply heal. It does not form scar tissue or accept the loss with resignation. Instead, it embarks upon one of biology's most complex and miraculous processes. It grows the limb back, completely, perfectly, as if loss were merely a temporary inconvenience. Within days of losing a limb, specialized cells called blastomal cells begin to accumulate at the wound site. These are cells that have forgotten their specific identity. They are no longer definitively muscle or bone or skin. They have returned to a state of pure potential, ready to become whatever is needed. It is as if the axolotl's body maintains a reservoir of stem cells so versatile, so responsive, that they can rebuild anything that has been lost. Over the course of several weeks, these cells organize themselves with a precision that defies understanding. Bone forms where bone should be, muscle where muscle is needed, nerve where nerve must grow. Blood vessels thread through the developing tissue like rivers finding their course. The skin seals perfectly over the regenerated structure, and in the end, the new limb is indistinguishable from the original, perfect in form, perfect in function. But the axolotl's regenerative powers extend far beyond limbs. They can regrow portions of their tail, their spinal cord, even parts of their brain. This is regeneration on a scale that mammals can barely comprehend. While we humans pride ourselves on healing a simple cut, the axolotl can rebuild complex organs, restore lost neural pathways, resurrect the very architecture of consciousness itself. Recent research from Universidad Nacional Autónoma de Mexico has revealed that axolotls can regenerate heart tissue without forming scar tissue, a feat that could revolutionize treatment for human heart disease. Their ability to restore severed spinal cords has made them invaluable to neuroscience, offering hope for paralysis treatment that was once considered pure fantasy. The secret lies partly in their unique genetic makeup. The axolotl genome, fully sequenced only recently, is massive, 10 times larger than the human genome, and packed with genetic instructions for reconstruction. They possess genes that are either dormant or completely absent in other vertebrates, genes that seem specifically designed for the art of rebuilding life. But perhaps more remarkably, they have retained the genetic memory of how to build every part of their body, even in their adult cells. While human adult cells are specialized and locked into their specific roles, axolotl cells maintain a flexibility, a willingness to change and adapt that we associate only with embryonic development. Part 3. The Aquatic Eden of Xochimilco. To understand the axolotl fully, we must journey to its birthplace, its only natural home in all the world, the lake system of Xochimilco, in what is now the southern part of Mexico City. Here, in the remnants of an ancient Aztec lake, the axolotl evolved its extraordinary characteristics over millions of years of perfect isolation. Xochimilco was once part of a vast lake system that dominated the Valley of Mexico. The Aztecs transformed these waters into one of the world's most sophisticated agricultural systems, creating artificial islands called chinampas, floating gardens that fed an empire. The canals between these gardens became highways of commerce and culture, and in their quiet depths, the axolotl thrived. The water here is cool and soft, filtered through volcanic soil and rich with nutrients. The canals are shallow and filled with aquatic vegetation, hornwort, water hyacinth, and native grasses that provide both shelter and hunting grounds. The water moves slowly, carrying the gentle current that axolotls prefer, never rushing, never forcing these delicate creatures to fight against harsh flows. In this aquatic paradise, the axolotl found no need to develop beyond its larval form. There were no seasonal droughts to force adaptation to land, no predators that could only be escaped through terrestrial flight, no environmental pressures that demanded the robust physiology of adult amphibians. Instead, the stable, nurturing environment of Xochimilco rewarded the axolotl for remaining exactly as it was, perfectly adapted to a world that asked nothing more of it than to exist in eternal aquatic bliss. The axolotl's daily life in these waters is one of patient hunting and graceful movement. They are predators, yes, but gentle ones, feeding on worms, crustaceans, insect larvae and small fish. Their hunting style is more ambush than pursuit, relying on their ability to remain motionless among the vegetation until prey ventures within striking distance. Their senses are exquisitely adapted to this underwater world. They can detect the slightest electrical fields generated by other living creatures, a ability that makes them formidable hunters in the murky waters where vision alone might fail. Their lateral line system, inherited from their fish ancestors, allows them to sense pressure changes in the water, feeling the movement of other creatures as vibrations through their bodies. Yet for all their predatory skill, there is something profoundly peaceful about watching axolotls in their natural habitat. They move with an unhurried grace, their external gills flowing like underwater plants, their lidless eyes surveying their domain with what appears to be ancient wisdom. Part 4. The Laboratory of Life. The axolotl's extraordinary biology has made it one of science's most valuable allies. In laboratories around the world, these creatures are helping unlock some of biology's deepest mysteries, offering insights that could transform medicine and our understanding of life itself. In the field of regenerative medicine, the axolotl has become the gold standard for understanding how complex tissues can be rebuilt after injury. Research published in journals such as Nature and Cell has revealed that axolotls accomplish regeneration through a sophisticated interplay of genetic switches, cellular signaling, and stem cell activation that we are only beginning to understand. Dr. Ellie Tanaka's work at the Research Institute of Molecular Pathology has shown that axolotl limb regeneration involves the creation of a structure called a blastema, essentially a growth zone that recreates the embryonic conditions necessary for organ formation. This process requires the coordinated action of hundreds of genes, many of which have been lost or silenced in mammals over the course of evolution. The implications for human medicine are staggering. If we could understand and harness the axolotl's regenerative pathways, we might be able to treat spinal cord injuries, regenerate damaged heart tissue, or even regrow lost limbs. The axolotl has become a biological Rosetta Stone, helping scientists decode the language of regeneration that nature has written in its genes. Mexican scientists at UNAM, Universidad Nacional Autónoma de Mexico, have been particularly instrumental in axolotl research, not only because of their proximity to the animal's natural habitat, but because they understand the cultural and ecological significance of preserving this remarkable species. Their work has revealed that axolotls possess an unusually stable karyotype. Their chromosomes remain remarkably consistent across generations, making them ideal subjects for genetic research. But the axolotl's contributions to science extend beyond regeneration. Their neoteny has provided crucial insights into developmental biology, helping scientists understand how genetic timing controls the progression from juvenile to adult forms. The discovery that axolotls can be induced to metamorphose into terrestrial forms through hormone treatment has revealed the genetic switches that control this fundamental biological process. In genetics laboratories, axolotls are helping scientists understand everything from cancer research to aging. Their ability to avoid the genetic damage that accumulates in most organisms over time has made them subjects of longevity research. Some laboratory axolotls have lived for over 25 years, maintaining their regenerative abilities throughout their extended lifespans. Part 5. The Shadow of Extinction. Yet for all its biological marvels, for all its contributions to human knowledge and potential medical breakthroughs, the axolotl faces a crisis that threatens to end millions of years of evolutionary success. In their natural habitat of Xochimilco, axolotls are disappearing at an alarming rate, victims of habitat destruction, pollution, and the introduction of invasive species. The International Union for Conservation of Nature lists the axolotl as critically endangered in the wild. Surveys conducted in recent years have found population density so low that some researchers fear the species may already be functionally extinct in its natural habitat, surviving only in the thousands of individuals maintained in laboratories and aquariums around the world. The ancient lake system of Xochimilco has been under assault for centuries. Spanish colonization began the process of draining the lakes, and modern Mexico City's water needs have continued this destruction. What remains of Xochimilco is a shadow of its former glory, a network of canals surrounded by urban sprawl, polluted by agricultural runoff and sewage, invaded by species that have no business in these ancient waters. Perhaps most devastating has been the introduction of invasive fish species, particularly tilapia and carp, which compete with axolotls for food and habitat. These introduced species are more aggressive, more adaptable to polluted conditions, and they reproduce more rapidly than the gentle axolotl. In the face of such competition, the axolotl's evolutionary strategy of patient specialization has become a liability. Research conducted by Mexican biologists has documented dramatic population crashes. In 1998, surveys found an average of 6,000 axolotls per square kilometre in Xochimilco's canals. By 2008, that number had dropped to 100 per square kilometre. The most recent surveys have found density so low that some canals that once teemed with axolotls now contain none at all. The threats are multifaceted and interconnected. Urban development has fragmented the canal system, creating isolated populations too small to maintain genetic diversity. Agricultural chemicals wash into the water from surrounding farmland, disrupting the delicate hormonal systems that control axolotl reproduction. Climate change has altered precipitation patterns, affecting water levels and temperature in ways that stress these highly specialized creatures. But perhaps the most poignant threat comes from the very success of axolotl conservation efforts in laboratories. While thousands of axolotls thrive in research facilities around the world, these captive populations have begun to diverge genetically from their wild ancestors. Laboratory axolotls, bred for ease of care and consistent research results, may no longer be capable of surviving in their natural habitat, even if that habitat could be restored. Conservation efforts led by Mexican researchers and international organizations are racing against time to preserve both the axolotl and its habitat. The Xochimilco Ecological Park and Plant Market has become a focal point for these efforts, working to restore native vegetation, remove invasive species, and create protected areas where axolotls might have a chance to recover. Part 6. Evolutionary Reflections. As we consider the axolotl's extraordinary life cycle, we find ourselves confronting profound questions about the nature of evolution, adaptation, and success. In a world that often equates progress with complexity, growth with improvement, the axolotl offers a different philosophy entirely. Sometimes evolution's greatest achievement is knowing when to stop. The axolotl's evolutionary strategy challenges our preconceptions about biological development. We are accustomed to thinking of larval stages as incomplete, as stepping stones to the real adult form. But the axolotl suggests that perhaps these juvenile forms are not incomplete at all. Perhaps they are complete in their own right, perfectly adapted to their specific niche, requiring no further development to achieve biological success. This is evolution as editor rather than author, choosing not what to add, but what to leave unchanged. The axolotl's neoteny represents a form of evolutionary conservatism, a decision to preserve and perfect rather than to continuously innovate. In their aquatic world, the axolotl found a form so well suited to its environment that any change would have been a step backward. Their regenerative abilities too represent a different evolutionary philosophy. While most vertebrates evolved to prevent cellular chaos through strict controls on cell division and differentiation, controls that also prevent regeneration, the axolotl chose to maintain the controlled chaos of embryonic development throughout life. They accepted the risks inherent in cellular flexibility in exchange for the ability to rebuild themselves when damaged. The axolotl embodies evolution's capacity for radical solutions to environmental challenges. Faced with a stable aquatic environment, they chose to abandon the standard amphibian life cycle entirely, creating their own unique path through the landscape of possibility. They demonstrate that evolution is not a ladder to be climbed, but a vast space to be explored, with countless solutions to the challenge of survival. Yet their current plight also illustrates evolution's limitations. The very specialization that made them successful in ancient Xochimilco has made them vulnerable to rapid environmental change. Their evolutionary bet on stability has been challenged by a world that changes faster than they can adapt. Perhaps most remarkably, the axolotl has become evolution's gift to consciousness itself. Through their contributions to scientific research, they are helping humans understand and potentially transcend our own biological limitations. the creature that chose to remain forever young may help us unlock the secrets of aging. The animal that perfected regeneration may teach us to rebuild our own damaged tissues. In this way, the axolotl's story becomes more than just another tale of adaptation and survival. It becomes a meditation on the nature of time, growth, and change. It reminds us that sometimes the most profound wisdom lies not in knowing when to grow, but in knowing when growing would diminish rather than enhance what we already are. Part 7. The Future of Wonder. As we look toward the future, the axolotl's story is far from over. In laboratories around the world, scientists are working to decode the genetic secrets that could make regenerative medicine a reality for humans. The axolotl genome, with its vast complexity and regenerative instructions, is being mapped and analyzed with ever-increasing precision. Research teams are developing new techniques for studying axolotl regeneration at the cellular level, using advanced imaging technologies to watch the process of regrowth in real time. They are identifying the specific genes and proteins that control blastema formation, the molecular signals that tell cells when and how to rebuild damaged tissues. Clinical trials are beginning to test therapies inspired by axolotl biology. Researchers are developing techniques to reprogram human cells to behave more like axolotl blastomal cells, potentially allowing us to regenerate damaged tissues. Gene therapy approaches are being designed to activate dormant regenerative pathways in mammals, pathways that were lost over millions of years of evolution, but might be recovered through careful genetic manipulation. The implications extend beyond medicine into our understanding of consciousness itself. As scientists study axolotl brain regeneration, they are uncovering clues about how neural networks rebuild themselves, how memories might be preserved or restored, how consciousness itself might be more resilient than we previously imagined. Meanwhile, conservation efforts continue in Xochimilco and in facilities around the world. Mexican researchers are working to create protected areas where wild axolotls might recover, removing invasive species and restoring native vegetation. Breeding programs are carefully maintaining genetic diversity in captive populations, preserving the biological heritage that millions of years of evolution have created. Educational programs are raising awareness about the axolotl's plight and importance, helping people understand that preserving this species means preserving possibilities for human medicine that we can barely imagine. The axolotl has become an ambassador for conservation, a living example of how protecting biodiversity protects our own future. Perhaps most importantly, the axolotl continues to inspire wonder. In a world that often seems to have catalogued and explained every mystery, here is a creature that still astounds us with its capabilities. The axolotl reminds us that nature still holds secrets we have barely begun to understand, that evolution still has surprises to reveal, that the living world around us is far more miraculous than we often remember to notice. Part 8. The Eternal Child. And so we return to where we began, to the quiet waters of an ancient lake where a remarkable creature glides through its aquatic world, unchanged by time, undaunted by loss, carrying within its cells the secrets of regeneration and renewal. The axolotl's life cycle, if we can call it a cycle when it seems more like a gentle, eternal curve, offers us a different way of thinking about existence itself. In choosing to remain forever young, the axolotl has discovered something that humans have sought throughout history: the secret of transcending time not by racing ahead of it, but by stepping gracefully outside its usual rules. In their external gills we see beauty in functionality, elegance in adaptation. In their regenerative powers we glimpse possibilities for healing that could transform human medicine. In their neoteny, we find a reminder that maturity need not mean abandoning the wonder and flexibility of youth. The axolotl teaches us that evolution is not always about becoming something new, but sometimes about perfecting something that already works beautifully. They show us that in nature, as in life, the most profound solutions are often the simplest ones. Finding your perfect niche and having the wisdom to stay there. As long as axolotls exist, in the canals of Xochimilco, in laboratories around the world, in the research that will grow from their remarkable biology, they will continue to embody one of nature's most hopeful messages, that damage need not be permanent, that loss can be restored, that the seemingly impossible might simply be a problem we haven't yet learned to solve. In the end, the axolotl's greatest gift may not be its regenerative abilities or its contributions to science, but its reminder that wonder still exists in our world, that creatures of impossible beauty and capability still glide through ancient waters, still carry secrets in their cells, still offer hope for futures we can barely imagine. The axolotl, forever young, forever mysterious, forever showing us that the most extraordinary life cycles are sometimes the ones that choose not to cycle at all, but to find perfection in a single, eternal moment of aquatic grace.